Not everyone is comfortable speaking in public. For some people, standing in front of any sort of crowd is a terrifying experience. Opening their mouth seems like a mistake waiting to happen. What if I don't say the right thing? Practicing the words only goes so far towards easing one's anxiety. There is a deeper psychological problem at hand which is ignored. There must be a better way to attack this problem head-on. Hello, I'm Daniel Nguyen, along with my team members Arye Ness, Ted Mosley, and Michael Trung. We are Group 61 of the Rutgers Spring 2020 Capstone Program. Throughout the semester, we've been advised by Dr. Agoravr.online, an expert in virtual reality therapy treatments. In this video, we will be going over the problem that invoked this project, our solution to the problem, our design choices, the tools and technical methods we use to implement our solution, and finally, any future work that could be done.
Before we can discuss our solution, it is best to provide some background for the problem at hand. Agoraphobia is an anxiety disorder that is characterized by being afraid of being in a scenario where a panic attack will occur, leading to an intense feeling of anticipatory anxiety. A very common example of this situation can be found when having to do any form of public speaking. This is known as glossophobia, or the fear of public speaking, and it is the largest subset of social anxiety disorder. 89.4% of people with social anxiety disorder have glossophobia. With social anxiety disorder impacting about 7.9% of Americans, this means that 7% of America suffers from this phobia, or about 23.2 million people. Furthermore, according to Columbia University, people with social anxiety disorder will make 10% less money than their peers, and are 15% less likely to get into a leadership or managerial position. What this means then is anyone suffering from glossophobia can expect to struggle in their professional careers, even if they have the skills to be making a lot more money. As a result of all this, we wanted to create a therapy option that was immersive, easy, and comfortable to use. With agoravr, we planned to solve all the problems associated with traditional therapy solutions. Our vision was to produce an affordable virtual reality solution which could help patients suffering from social anxiety from within the comfort of their own home. To accomplish this, we had decided to develop a solution around the Oculus Quest. Provided its relatively low price tag and ease of setup, it was the ideal device to develop for. To keep track of the patient's progress to our treatment, we developed an online web portal to store data from each session. The web portal is a place where the patient and their clinician have access to an audio recording of the session, as well as heart rate and blood oxygenation data collected throughout. The patient would be able to play back an audio recording of the completed session to review themselves and be able to view the biodata collected to see an objective measure of their stress. Likewise, the patient's clinician could review both the audio and the biodata to review how the patient performed and recommend how the patient should proceed. To get valuable external feedback, we add the optional role of caregiver. The caregiver is typically a close family member or friend that is given access to session data by the patient. Using this data, the caregiver can provide more personal insight and feedback regarding the patient's condition and progress. After a patient performs a session, any associated data we recorded is uploaded to our server. This data will be made available for each of the users with permission to view it. Using this feedback, we can control the patient's progress in multiple ways. One way is an automated state machine integrated into the system. Another way is for the clinician to manually adjust settings for the session. By utilizing a state machine, where every node has a different level of difficulty, the patient can either progress and move up a difficulty level, or return to a lower level of difficulty if they performed poorly. This is an automated system with strict, predefined states, so having a manual override provided to the clinician gives them more control and allows them to customize the session to the patient's current status. Finally, we planned to test our solution through a clinical trial with patients experiencing social anxiety. This would allow us to test whether patients diagnosed with agoraphobia would find our solution helpful or not. Before each session, we would survey the patients on how anxious they're currently feeling. Then, through a series of 3 30-minute sessions, the patient would complete a variety of scenarios in our virtual reality environments. Afterward, They would review their experience to give us more insight into what our solution was doing right or what it was doing wrong.
In order to make our solution a reality, we needed to research, design, and implement all of the required features. I will be discussing these 3 steps in detail to illustrate our design process and what we have produced so far. For our VR application, we developed 2 scenarios to simulate variable-sized public speaking environments. We chose to create public speaking scenarios because it is a very common fear for many people who suffer from agoraphobia. We will use these scenarios to simulate exposure therapy in a controlled way. The first environment that the user will experience is the meeting room. The meeting room is a small room with a maximum capacity of around 5 individuals. This scenario simulates a more close and personal presentation and will serve as a starting point for new users. The second environment is the auditorium. The auditorium is a TED Talk inspired environment with around 700 seats. This environment is a step up from the meeting room as the user is exposed to a larger scaled audience. Prior to each session, the patient will have a briefing on what they are presenting and can prepare themselves in advance. After a few minutes or when they are ready, the session will begin. In the meeting room scenario, the user will present slides on a TV screen behind them. In the auditorium scenario, a script will be displayed on the teleprompters for the user to read. In front of them is a smaller screen for when they also need to present slides. By the end of the session, the user will be graded on factors such as how loud and accurate they spoke, head and hand movements, eye contact, and their overall stress level. If the user passes, they will proceed on to the next session, which increases in difficulty. The recorded audio will be saved to an audio file that can be accessed on the session summary on the web portal. We also decided to implement speech-to-text translation. This allows the clinician to read what the patient said without having to listen to the entire audio file. On the web portal, the clinician can make a side-by-side comparison of the original script and the translation. Additionally, the translation will be compared for accuracy with the original script. We are measuring the accuracy as a percentage, which is one of the factors for determining if the user passes. The difficulty increases by providing a longer script, adding a slideshow they need to click through, increasing the number of audience members, and the frequency of the distractions. All of these factors will be saved to the session and can be viewed on the web portal as a graph over time. We have created several different animated distractions to make the audience feel alive and more realistic. There are several different types of distractions, including coughing, sneezing, laughter, yawning, and side conversations. We also wanted to see how the user behaves when increasing the number of distractions. We accomplished that by tracking the eye contact, head movement, and the user's microphone level when a distraction occurs. Each distraction is timestamped and saved on the graph on the web portal. This allows the clinician to directly see the patient's reaction to these events. We needed a way to measure the patient's heart rate and blood oxygenation and receive the information in our application. We will use this data to determine the patient's stress level. To do this, we attached a sensor to the patient's earlobe and connected it to an Arduino. This Arduino will control the sensor and read and process the data. We can then transmit the data via Bluetooth. The data is received by our application on the Oculus Quest, which allows us to keep track of the patient's stress level in real time. The data is time-stamped, which allows the clinician to review the data via the web portal, along with all the other data that we saved. The deployment of the web portal is accessible with the URL agoravr.online. New users can create an account by entering their full name, username, and password, followed by choosing the appropriate account type. New patients have direct control over who is authorized to view their session data. By sending a request to a clinician or caregiver, the patient grants them access to view their session data. Logging into the web portal provides the patient with a view containing multiple cards. The top card shows the user a table containing all of their past sessions. Below this are cards for viewing and managing clinicians and caregivers who have access to the session data. Let's send a request to our new clinician. Viewing the clinician page, we can accept the request. Our list of patients is updated, allowing the clinician to view each patient's session. The session view lets the user with access inspect data about their session. Here, the audio of the session can be played back. The script, as well as the speech-to-text result, can be viewed side by side. Below, there is an informational chart containing data from the session. This is where the patient's heart rate is graphed, as well as their speech volume. Overlaid on the graph are a series of rectangular areas showing when specific distractions occurred during the session. When compared with the heart rate and volume data, we get an objective idea of how the patient reacted to these distractions and the session overall. Specific region of the graph can be focused on by selecting a region on the lower graph. The filter can be removed by right-clicking on the filtered region.
Now that we've discussed all of our product's features, it's a good time to briefly discuss the tools we use to make it happen. Our VR application is built around the Oculus Quest. This head-mounted display integrates a system running a modified version of Android 7.1 for rendering. The Quest provides access to Bluetooth through Bluetooth Low Energy, BLE for short. The lower energy protocol significantly reduces the power usage, making it great for battery-powered devices. To develop on the Oculus Quest, we decided upon using Unity 3D, along with its support for the Oculus SDK. To create 3D models, we decided upon using the open-source modeling software called Blender. To produce a Bluetooth heart rate monitor, we needed to connect a heart rate sensor to a development board. For our sensor, we chose the Maxim Integrated RevDes 117. As for the development board, we chose the Arduino Nano 33 BLE. Communication between the sensor and board is handled using the I2C serial protocol. To receive BLE transmission on the Quest, we wrote a native Android plugin which wraps the Android BLE API. Unity can call functions defined in this plugin, thus retrieving the heart rate data over BLE. This is recorded to a CSV file for graphing. Using the Quest's built-in microphone, we record the user's speech to a WAV file. Using NAudio, a C# audio library, we compress the file to MP3 for later playback and storage. The magnitude of the captured audio is sampled 10 times per second to a CSV file for graphing. We also analyze the user's speech using the cloud service IBM Watson speech-to-text. A percent accuracy is calculated using the Damrau-Levenstein algorithm. Using the Quest and its controllers, we are able to track head and hand movement. All of the data we collect is transmitted to our server via our REST API. The back end of our software stack consists of an asynchronous Python HTTP server acting as a REST API in front of a PostgreSQL deployment. Using AIO HTTP, we are able to create REST API endpoints extremely quickly. Using the async PG driver, we are able to query our PostgreSQL database asynchronously. Authorization is handled using JSON Web Tokens. After authenticating with the server, the user may use their token to access specific endpoints until the token expires. The web portal was built using the Svelte JavaScript framework. This framework generates static JavaScript at build time and also allows the developer to break their HTML and CSS into reusable components. Each individual view is populated with data retrieved from the REST API. Graphing is handled using D3, a JavaScript library for making highly customizable charts. Finally, our REST API and web portal are deployed behind an Nginx reverse proxy running on a Linode VPS. The site is publicly accessible via agoravr.online. While we were able to develop many solutions during the semester, there are a number of ways we have considered taking agoravr in the future. We were unable to execute the research study we had been developing. Due to the COVID-19 pandemic, Rutgers University discontinued all research with human subjects, forcing us to temporarily halt our study. A study would provide us with valuable feedback from users on the effectiveness of our solution or any possible improvements. We chose to focus on the public speaking aspects of agoraphobia, but this only encompasses a small subset of social anxiety triggers. We would like to add more scenarios as well as improve the fidelity of our existing scenes to provide more effective treatment. Another possible source of objective data we could take advantage of is blinking. Research shows that an increase in blinking is an indication of stress. Placing an infrared camera in the headset and using computer vision, we could track and record blinking. IBM Watson provides a tone analyzer service. We could use this to analyze the patient's speech and give yet another objective source to detect stress.
Thank you for taking your time to watch our video. We hope that you found our idea compelling and our implementation innovative. We are excited to speak with you during our Q&A session on April 30th.